Okay, any questions? Any other questions? Now, let me also just summarize our kind of where we are trying to go. If you remember the Helmholtz theory, we had defined this property called the electric field. Basically, if we know the electric field, then we know the forces acting on the charges. If we know the forces acting on the charges, then we can determine how the charges will move, etc. So we can determine kind of everything. So that's why we are studying the electric field. Then the question is how we calculate the electric field. If we know all the charge everywhere, then we can just evaluate the integral that gives us the electric field, and we are done. But in most cases, we don't know the charge distribution everywhere. What we know is we know the charge distribution in a certain region, plus some boundary values of the electric field or the potential at the boundary of this region. We don't know what the electric charges over here are. So that kind of doesn't allow us to use that integral expression for the electric field. So we would rather find some properties of the electric field, let's say, that are local. Well, local expressions are derivatives. The differential equations are local relationships between the properties of a given quantities. And so what we had seen was, okay, there is this electric field that we want to evaluate. There is the Helmholtz theorem, which states that if you know the divergence of a vector field and the curl of the vector field, plus the, let's say, some suitable boundary conditions, then we can solve for the electric field, and we will see that the electric field is unique. And now we calculated what the divergence of the electric field and the curl of the electric field are. So Helmholtz theorem tells us that since we know the divergence of the electric field and the curl of the electric field, we should be able to determine the electric field itself. And then, of course, we can, in principle, determine, but it's just like the mathematicians saying that there exists a solution. So, and for a mathematician, that's usually the end of the story. For us, it is the beginning of the story. Okay, there is a solution, fine. So what is the solution? Now we need to solve these two equations, impose our boundary conditions. Now the potential, the definition of the potential is in fact solves one of these equations. So since we know that the curl of the electric field is 0, the solution of this equation is the gradient of some scalar function. You just give me some scalar function, any function you like. I take the gradient, and that vector field has curl 0. So one of the equations is already solved. There's still the other equation that we need to solve. We need to solve that this divergence of the electric field should be equal to 0. So this, whatever this V is, the gradient of V solves this equation, whatever the V is. But whatever V is, the obtained electric field will not solve the divergence, the Gauss law. So this basically tells me that, okay, the electric field, from this equation, we know that the electric field can be written as the gradient of some function, but that function should be a special function, and it should satisfy the Poisson's equation. Now we had converted our equation. Now before we had the divergence of the electric field gave us one equation for the three components. The curl of the electric field gave us three equations for the three components of the electric field. So we had 4 equations to solve for the 3 components of the electric field. Now we reduced all those 4 equations into a single one. We already solved, in a sense, the 3 of them. There's a single equation left to solve. If we can solve this equation, subject to the boundary conditions, whatever boundary conditions we have, well, most of the time the boundary condition will be the potential at infinity should be 0. That's our boundary condition, for example. If we can solve this equation for that boundary condition, we are done. We know the potential, and taking the gradient of the potential, we know the electric field. And that is what we will be doing. Of course, it turns out that this potential has other properties, like when we will study the energy stored in given charge distribution, we will see that we can express that energy in terms of its potential. But we will also see that we can express the energy stored in terms of the electric field. Because basically the potential and the electric field, they carry exactly the same information. You can express one in terms of the other one. So this is how you can relate the potential to the electric field, and V is equal to that integral is how you can relate the electric field to the potential. They are related to each other. And each one contains exactly the same amount of information about your physical system. Any questions?
Yani hocam biz şu 4 denklemi mi çözmeye çalışıyoruz?
We are trying to solve these equations. We have these, well, this is just a single scalar equation. That is a vector equation. A vector equation has, in principle, 3 components, let's say, plus the boundary conditions. And we need to solve these differential equations for all 3 components of the electric field. Let's do some examples of the potential. Let's take the ring. We have a ring of radius r. It has a total charge q. Again, for simplicity, let's take this point just on top of the center of the ring at a distance d. What will be the potential? So shall we use Cartesian coordinates, spherical coordinates, cylindrical coordinates? Cylindrical, okay. Well, we will not be using any one of them, in fact. Let's say we have this charge, this segment of length, let's say dl. It has a charge dq. We are assuming that the charge is homogeneously distributed over the ring. So the charge per unit length times the length of our segment is the charge of our segment. We need this distance r. And small r is nothing but square root of r squared plus d squared. So the potential is just the sum of the potentials created by all of those segments. It's the sum of q over L dl. This is the charge of that segment. 1 over square root of r squared plus d squared is the distance of that segment from our observation point. And then we have the 1 over 4 pi epsilon 0, the overall constant. Well, as we sum over all these segments, q is constant. L is the total circumference that is constant. R is the radius of the ring, which is constant. D is the center from the distance from the center of the ring, constant. Well, these are constant. All constants we can take out. Q over L, 1 over r squared plus d squared, 1 over 4 pi epsilon 0, integral of dl. Well, again, the integral of dl is nothing but the sum of the length of each one of these segments, which gives me the total circumference. Large L was also the length of the circumference, so they just cancel each other. So the potential at that point is nothing but Q over 4 pi epsilon 0, 1 over square root of R squared plus D squared. If you remember how we solved the electric field at that point, we had to consider the horizontal component, the vertical component, etc., then show that the horizontal component was 0 and calculate the vertical component. But here in the potential, it's just a scalar function. It's just a sum of numbers. So we don't have to worry about the horizontal component, vertical component, etc. We are done. This is our potential of this ring created at that point D, at a distance D. If we want to calculate the electric field, the electric field is minus the derivative with respect to x in the x direction minus the derivative of v with respect to y in the y direction minus the derivative of v with respect to z in the z direction. But the problem is here in this expression we already set x is equal to 0 and y is equal to 0. So we don't know how this expression, how this potential depends on x and y coordinate. So we cannot take the x and the y derivatives. But what we can do is we can take the z derivative, because the z coordinate of that point is nothing but d. So the z component of the electric field is equal to minus dv by d in the z direction. This is equal to, well, if you just take the derivative, you get minus q over 4 pi epsilon 0, then minus 1 over 2 twice d divided by r squared plus d squared to the power 3 halves. So minus minus go away, 2's cancel. This is q over 4 pi epsilon 0, d over r squared plus d squared to the 3 halves. This is our electric field, the z component. Well, the x and the y components, we cannot really evaluate it from this expression just by looking at this expression, because we don't really know what the x and the y derivatives are at that point. But nevertheless, just by looking at the symmetry of your problem, you can claim that the x and the y derivatives are 0. We know the z component. We know all the components of the electric field, so we know the electric field. Let's do another problem. Let's imagine we have a plus q charge over there and a minus q charge over here, separated by a distance d. This is their separation, and we would like to find the electric field at this point r. Well, if you look at the electric fields created by each one of the charges, the positive charge will create an electric field in this direction. The negative charge will create an electric field, let's say, in this direction. The sum will be an electric field somewhat in this direction. Then, of course, expressing the x, y, and z components of the electric field will not be easy. Let's look at the potential. Let's say that this distance is r plus, this distance is r minus. The potential at the point r, this is equal to q over 4 pi epsilon 0, 1 over r plus, plus minus q over 4 pi epsilon 0, 1 over r minus. R minus is the distance of that point from the negative charge. R plus is distance from the positive charge. Or the potential at the point R, this is equal to q over 4 pi epsilon 0, 1 over r plus minus 1 over r minus. Or this is equal to q over 4 pi epsilon 0 r minus minus r plus over r plus times r minus. Okay, now what is r plus, what is r minus? Now let's define this vector d, or let me call it delta. Delta is the vector from the middle to the positive charge. If we choose this to be the z-axis, then the delta vector is nothing but d over 2 in the z direction. And this is our origin. Now, if you look at these vectors, r plus vector is nothing but r minus delta. If you take the minus delta, consider the minus delta vector, that is this vector pointing from the positive charge to O, then you add the vector from O to our observation point, so that is nothing but r plus vector. R minus vector, on the other hand, it is r plus delta. So this is delta, you add the r, you get the r minus vector, pointing from the negative charge to our observation point. So r plus, which is the magnitude of this r plus vector, which is the square root of r plus vector squared, which is square root of r minus delta vector squared. So this is equal to the square root of, well, let me just do both of them together. They look basically the same. If you take the lower sign here, take the lower sign everywhere. If you take the upper sign here, take the upper sign here, upper sign here, upper sign here. That will be the notation. Square root of r squared plus delta squared. Well, I have the square of this one, the square of this one. So these two terms do not depend on this sign. Then I have the plus or minus twice the product of those two. Plus or minus twice r times delta times cosine theta. I have the scalar product of two vectors, which is defined as multiply their magnitudes, multiply by the angle between the two. Which is equal to, let's say, r times 1 plus delta over r squared plus or minus twice delta over r cosine theta raised to the power 1/2. Now, up to this point, everything was exact. I didn't make any approximation. So whatever this point P is, wherever it is, this result, these results that we obtained are correct. Now we will make some approximations. I will assume that this point P is very far away, meaning that or either the point P is very far away or these plus or minus charges are very close to each other. How close? Think of these positive and negative charges as the charges in an atom, the positive and negative charges. So this D is the atomic size. And we can only look at the atoms at distances that are tens of the atomic size. So that's kind of the magnitudes. So we will assume that D over R is much, much smaller than 1. But if D over R is much, much smaller than 1, that means this number over here is much, much smaller than 1. This is very small. This is even smaller. And for very small numbers, I know that 1 plus x raised to the power n is equal to 1 plus n times x. Now I will use this one, approximately. So r plus or minus is equal to r multiplied with 1 plus 1 over 2 times delta over r squared plus or minus twice delta over r cosine theta. Of course, approximately. Now, I said that, no, not, yes. Now, d over r is very small. Remember, delta is nothing but d over 2. Delta over r is very small. This is very small, like, let's say, 10 to the power minus 1. This is even smaller, 10 to the power minus 2. So I will just ignore this one. I will keep only that one. So r plus or minus is approximately equal to r 1 plus or minus delta over r cosine theta, or which is r plus or minus r delta cosine theta, or r minus plus is approximately equal to r plus or minus now there is no r over here, r dot delta over r. Just approximately. It gets this approximation gets better and better the smaller this ratio is. Now let's see. This is our potential. We know what r minus is. We know what r plus is. This is equal to q over 4 pi epsilon 0 r scalar product with twice d divided by r. This is r minus minus r plus. When I take this difference, one comes with a plus sign, the other comes with a minus sign, so that's why I have that too. Times 1 over d 1 over r squared plus, this is just an approximation. There are corrections to that, but those corrections will be proportional to d over r squared, because I just ignore anything that contains additional factors of d over r squared. This term, this first term, is already proportional to, remember, this is d. This term is already proportional to d over r. Plus, there are other terms that will be proportional to d over r squared, d over r cubed, d over r to the fifth, etc. But if d over r is very small, I can just ignore them. Now, we usually define what we will call a dipole moment as q, the charge, times the vector separating these two charges, which is twice the delta. This is that definition. Now, in terms of this charge, V of r, the potential created by this configuration at a very large distances is q over 4 pi epsilon 0 p dot r, no, there is no q, 1 over 4 pi epsilon 0 p dot r divided by r cubed. This is our potential at every point, at any point. Well, once we know the potential, we can evaluate the electric field at every point. You see, if you wanted to calculate the electric field at every point, you could in principle. But of course, in that case, you have to calculate the components of this vector and the components of that vector and sum them up, etc., and try to combine them. But now I didn't have to bother about the components. Well, some of the derivations might look some kind of tedious. They are tedious. They're not complicated. Just the basic principle is that I just use this approximation. And once you do that approximation, in just a couple of lines, you get this result over here, this potential. So we know the potential. This is at an arbitrary point. And once you know the potential, you can calculate the electric field at an arbitrary point. In fact, you should have done this in your first year. I had given you the potential without saying you where it came from, and you were supposed to calculate the electric field, if I'm not wrong. Any questions on this one? Okay, let's do another example. Before the dipole, we had the potential created by the ring. Now let's look at the disk. We have this disk. It has, let's say, radius r. And again, we would like to calculate the potential at this point, P, that is at a distance d from the center of the disk. Now we can, of course, just as in the case example of the ring, we can divide this disk into very small squares, let's say, calculate the potential created by each one of those squares and sum them up. That is one possibility. But we already know the result of the ring. We can also use that one. So we can just imagine this disk as being a collection of some very thin, many rings. Now let me take one of those rings. Let's say it has a radius r, small r, and the thickness dr. The disk has a uniform charge, and the total charge is q. So what is the charge of this ring? Well, the total charge is uniformly distributed over the area. Pi r squared is the total area. So the charge per unit area is given by the charge divided by the total area, which is pi r squared. So what is the area of this ring? Well, these are my parameters. I have the radius, I have dr, that's all. You should be able to express, these parameters uniquely define this ring, so you should be able to express the area of the ring in terms of these parameters only. Well, integrate over phi. That will be your answer. What you stated was, if you imagine such a small region, the area of this region is dr r d phi. If you sum over all the possible phi values, it gives you a 2 pi. Or, as your friend pointed out, you can just imagine this ring opening up this ring. If you open up the ring, it just becomes a rectangle, almost a rectangle. And the area of the rectangle is nothing but the product of two sides. One of the sides of the ring is the circumference of, one of the sides of this rectangle is the circumference, which is 2 pi r. And the other side has length dr. So this is the charge of this very small ring. Now, we know the charge of this ring, we know the radius of this ring, so we can just write down the potential of that ring. dV will be equal to 1 over 4 pi epsilon 0 times the charge of the ring. Let's go back to our previous example. You see the potential is 1 over 4 pi epsilon 0. This is the charge of the ring. This is the distance of the ring from that point. Not distance of the center, but distance of one of the points on the sides. So let's go back. 1 over 4 pi epsilon 0 is the overall constant. We have the charge, which is q over pi r squared times 2 pi small r dr. 1 over the distance of each one of these, a given point on the ring from my reference point, but that is nothing but square root of small r squared plus d squared. This is our dV. Now we can just sum all these contributions from the ring. So V will be equal to 1 over 4 pi epsilon 0 integral of q over pi r squared 2 pi r dr divided by square root of r squared plus d squared. And the radius of the ring starts from 0 and goes to the capital R, which is the radius of my disk. You see, this was an arbitrary ring. I'm just summing over all these rings, and the smallest ring has the radius 0, the largest ring has the radius of the disk. So that's how I determine the limits. These. Let's calculate that integral. This is one of the easy integrals, although it might not look like so. You see, the integrand is nothing but the derivative of square root of r squared plus d squared. If you take the derivative of this function over here, you get r over square root of r squared plus d squared. And of course here the small r changes from 0 to large R. And let's do some simplifications. 1 over 2 pi epsilon 0 q over r squared square root of r squared plus d squared minus d. This is the potential of our disk. Or let me just do one more aesthetic change. 1 over twice epsilon 0 times sigma times square root of r squared plus d squared minus d. This is our potential, where sigma is nothing but q over pi r squared. Now what I did was, here I have a factor of q divided by pi r squared, which is the total area of my disk. So this sigma is nothing but the surface charge density of my disk. So the q over pi r squared. And these are the remaining factors. So we started with the potential of a unit charge. Then we obtained the potential of the ring. And by just adding rings, we obtained the potential of a disk. Of course, these are along the axis of the disk or axis of the ring. If you want an infinite plane, well, if you just take the size of the ring to be larger and larger, it starts to look like an infinite plane. So the potential of an infinite plane would be nothing but the potential of a disk in the limit as r goes to 0, r goes to infinity, sorry. What happens if r goes to infinity? Keeping sigma constant? Sigma is constant, 2 epsilon 0 is constant. We are taking the limit as r goes to infinity. to obtain the potential of an infinite plane. The charge also goes to infinity. So that sigma is constant. R goes to infinity, Q goes to infinity, sigma is infinite, it's constant. What is the potential? Oops. So what's wrong? You see, we already studied the problem of an infinite plane. We know what the electric field of an infinite plane is. And corresponding to that electric field, we should be able to write a potential. Right? That if in principle, we should be able to obtain the same potential starting from a disk. Just take the disk larger and larger. Eventually, it will look like an infinite plane. But somehow it didn't work. Correct. You see, that was one of the assumptions. We had said that at infinity, since there is no charge, we can naturally set the potential to be 0. That is why we are choosing the infinite point as our reference point. But if you have an infinite plane, the charge at infinity is not 0. So you cannot really set the potential at that point to be 0. This is correct. Let's obtain the infinite limit, the potential of an infinite plane. But we have to change our potential, reference point. So rather than, you see, in a sense, this is the potential difference between a point along the axis of our disk at a distance d from the center of the disk and a point at infinity. This is the potential difference corresponding to those 2 points. But we cannot set the potential at infinity to 0 now. Rather than that, what we can do is potential of infinite plane. So let's say this is the point A, this is our point P. Instead of choosing the point at infinity to be 0, let's choose the potential at the point A to be 0. Then the potential difference, Vp minus Va, you see potential difference is independent of our reference point. So we can calculate this potential difference using our previous expression. So this was our previous result. This is equal to, this is the potential at the point P. Well, the potential at the point A, what is the potential at the point A? No. You see, this result we had obtained by taking the reference point at infinity. So with this result, the potential at the point A is non-zero. But the potential at the point A is the point for which D is equal to 0. So if you set D is equal to 0, this is just R. 1 over 2 epsilon 0 sigma times R. Now, this is a result that we obtained using our previous result. Our previous result was based on the assumption that we set the potential at infinity to 0. But when we look at potential differences, our reference point does not make any difference. So whichever reference point we choose, this potential difference has to be equal to this expression, whatever our reference point is. Now we can set VA to 0. Choose A as our reference point. Now, the choice V at A is equal to 0 is our choice. You could have just said that the potential at the point A is 5 volts. It's your choice. You can make that choice. But just for simplicity, if we just set it to 0, Then this is the potential at the point P. Of course, this is still the expression for a finite disk of radius r. Now we are going to take the limit as r goes to the infinity. So what happens when we take the r goes to infinity limit? How? Well, this is infinite, but infinite minus infinite is indeterminate. You cannot really say what it is. You have to take the limit in a suitable way. No, sigma will stay as sigma. Sigma is constant. Q will go to infinity if we put it there, or pi r squared will go to infinity. Q over pi r squared will be kept constant at the value of sigma. So sigma is there just as a constant. How do you take this limit? The limit of that difference. Well, there are various means you can do it. Multiply it with the plus sign, divide by the plus sign. If you multiply it with the plus sign, you get r squared plus d squared minus r squared cancel, etc. But we know the Taylor expansion. Taylor expansion will be your best friend, even in these limits, in these cases where you have indeterminate limits. Let's see. We are taking the limit r goes to infinity. Now, square root of r squared plus d squared is square root of r 1 plus d over r squared. Well, you see, d and r will go to infinity. D over r is a very small number. We can use our expansion. This is approximately equal to r times 1 plus 1 over 2 times d over r squared, which is approximately equal to r plus d squared over twice r. So v at the point P is equal to 1 over 2 epsilon 0 sigma r plus d squared over 2r minus d. This is almost, well, these cancel. If you take the limit r goes to 0, also this term goes to 0, so there are no corrections to 0. So basically you were right. The difference goes to 0 in this case. This cancels this one, this goes to 0. We are left with minus d. Or let us rewrite it in a different form. What is d? In terms of the coordinates of our point, no? You see, the point A has the coordinates x, y, and 0. It's not z, it's the absolute value of z. Well, there's the sigma. So we know the potential. What about the electric field? Or let's say that V of P is equal to sigma over 2 epsilon 0 times minus z if z is larger than 0 plus z if z is less than 0. It won't depend on the x and the y components. So the electric field minus dV by dz in the z component This will be equal to sigma over 2 epsilon 0 z hat if z is larger than 0 minus z hat if z is less than 0. Now, the electric field, is it continuous across this sheet? Just below the sheet, if you approach z from below, it is pointing in the minus z direction. If you are approaching z equal to 0 from above, it is pointing in the plus z direction with the same magnitude. Just the directions will be different though. So the electric field at z equal to 0 changes instantaneously as you cross the z equal to 0 plane. What about the potential? Is the potential continuous? No. What happens to the, what is the value of the potential as you approach z is equal to 0 from below? What is the value of the potential?
Minus sigma. İşte şu.
What is the value of absolute value of z as you are approaching z is equal to 0 from below? What is the value? You are approaching 0. Z is equal to 0. You are looking at that point. Yes. If you are approaching the point z is equal to 0 from below, the potential is 0. If you are approaching the z is equal to 0 from above, the potential is 0. So is it continuous at z equal to 0? The potential is continuous. You see, the electric field is discontinuous across this sheet, charge sheet, but the potential is continuous. Yes. Now we are driving the boundary conditions. You see, on last week we had shown that the electric field at the top minus the electric field at the bottom, they were different. Well, the parallel component was continuous, but the component parallel to the surface was continuous, but the perpendicular component was not continuous. And we could write the same thing as sigma over epsilon 0 in the n direction, where this n vector just points from bottom to the top. Well, we actually see it over here. You see, if you, above the plane, the electric field is sigma over 2 epsilon 0. Below the plane, it is sigma over minus sigma over 2 epsilon 0. If you look at the difference is sigma over epsilon 0 in the z direction. So it's basically this statement over here. If you would write the same expression for the potential differences, the potential just above the surface minus the potential just below the surface, this is equal to minus E dot dl from bottom to above. Yes, the electric field is not continuous, but it is finite. It doesn't become infinite. dl from just below to just above, it goes to 0. So you are integrating a finite function over an interval that has 0 thickness, 0 size. So this is just 0. So delta V across the surface is 0. The potential is always continuous across a charged sheet. But the electric field, that is its derivative, is not continuous. The derivative of V in the direction normal to the plane, evaluated at the top, minus the derivative of v in the normal direction again at the bottom. This is equal to minus sigma over epsilon 0. So eventually, we will have studied the electric fields in different media. We already know the one boundary condition, at least, that the potential at infinity should be 0. That is one boundary condition. But let's say if you have glass over here, eventually we will study light. If you have glass, well, there is some electric field inside. There will be some electric fields outside. They should be related somehow. And the relations are here. The potential at the boundary of this glass should be continuous, but its derivative should be discontinuous, and the potential at infinity should be 0. Those are the boundary conditions we have. Now, when we are solving for the potential, when we are solving the Laplace's equation, these will be the boundary conditions we will be using.
Hocam şimdi şu integral sıfıra eşit dedik ya.
True.
Bu yani şeyi mi vurguluyor? Equipotential line'ları mı vurguluyor?
No, there's no equipotential line. We are only looking at, we have this surface. I'm just comparing, calculating the potential difference between this point and this point. The thickness eventually goes to 0. So that is why the L goes to 0. So the potential difference will be basically the electric field here multiplied by the separation of those 2 points. But the separation goes to 0. The electric field is finite. I mean, you see, if the electric field would go to infinity, I couldn't have set that to 0. Because in that case, I would have, okay, infinity times 0, which is indeterminate. It can have any value. But I know that the electric field is finite. The separation is 0. So that integral, the electric field multiplied by the separation is 0. The electric field, yes. At a single point, you cannot really define it. You can choose it to be 0, for example. It's up to you. But that doesn't make any difference. And as long as your function is finite, the value if you change the value of your function at a single point, it doesn't change the integral. In real life, what you will have is, of course, the sheets will have some thickness. So the magnitude of the electric field, you see, the electric field, the Z component will change from sigma over 2 epsilon 0 to minus sigma over 2 epsilon 0 smoothly. I mean, from here, it won't just jump over here, but it will be smooth for physical surfaces. So there's no risk that at that point where we don't define the electric field, it cannot have an infinite value. Well, you see, okay, this was one problem where we, as you said, we assumed the boundary condition was that on the plane, the potential is 0. And so we obtained the full solution of our potential. Now, this is a general problem. We don't necessarily have an infinite plane. We have an arbitrary surface. We don't know what we take the value of the potential at that surface. I mean, the potential at every point on the surface can even be different. But whatever your problem is, the potential across every point on the surface should change continuously. The potential cannot jump from one value to the other value. But the derivative, that is the electric field, it can jump from one value to the other value if there are some surface charges. So that is the lesson of the story. This was just, in a sense, this is just a simple application of these more general conditions. These conditions should be satisfied for any surface that you can imagine in electrostatics. Any other questions? Okay, so tomorrow, no recitation. And so we have our lecture on Friday. Don't forget your homeworks for Friday. I will pick them up at the beginning of the first lecture.
Klasa yüklemiyoruz.
Yok, onları buraya getiriyorum.
Hocam bir de
Yani bilgisayarda yazıp getirirsen hiç itirazım olmaz.
Odanızda olacak mı?
Ankara'da değilim yarın. Ankara'da değilim yarın.
hocam şeyi soracağım. Bir point charge'ın herhangi bir noktada yol açacağı potansiyeli hesaplayıp formülize etmek lazım.
Evet.
Peki birbirine çok yakın artı ve eksi iki yükün herhangi bir A noktasında oluşturacağı potansiyeli daha karmaşık bir şekilde hesaplamak bize ne getiriyor mesela?
Hesap